Okay, we're going to pick up our discussion of finding limits using analytic methods by looking at one-sided limits. Going back to the problem that we did in the previous video, there was a vertical asymptote at 4. So how can we determine the behavior of the function at this value? So just to recall, let me rewrite the simplified form of our function. So we have the limit as x approaches 4, in this case from the right. We have x plus 3 over x minus 4. So we can see we have the vertical asymptote. So what we notice is that as x approaches 4 from the right, if you pick a value a little to the right of 4, you can analyze that value and see, are you headed to positive infinity or negative infinity without actually having to graph the function. So in this case, I'm going to pick the value x equals 4.1. And I'm going to evaluate the limit at that point. So I am going to take the limit as x approaches 4.1 of x plus 3 over x minus 4. I'm going to look at that value. Excuse me. So what I have is 4.1 plus 3 over 4.1 minus 4. When I simplify this, I get 7.1 over 0.1. And what I want you to notice is the fact that we have a positive number over a positive number. So that means that as x approaches 4 from the right, y is going to approach positive infinity. So we can say then that the limit of the function, oh, it's already written there for me. I have to write it again. So we can say that the limit of the function f of x as x approaches 4 from the right is going to be positive infinity. So we can do the same thing on the left-hand side. So what we have again, our simplified function, is going to be the limit as x approaches 4 from the left of x plus 3 over x minus 4. And again, we are going to pick a value as x approaches 4 from the left of the simplified function and see how its behavior is, because we know we have an asymptote, a vertical asymptote there. So on the left of 4, which direction? Is it going to go also to positive infinity, or is it headed to negative infinity? So in this case, I'm going to pick the value x equals 3.9. So I'm going to find the limit as x approaches 3.9 of x plus 3 over x minus 4. So substituting, I get 3.9 plus 3 over 3.9 minus 4. So I'm going to get 6.9 over negative 0.1. So this time I have a positive value over a negative value. So I can see that as x approaches 4 from the left, y is approaching negative infinity. So I could say that the left-hand limit as x approaches 4 of f of x is going to be negative infinity. So that's how you can handle a left or right-hand limit or a vertical discontinuity, which is a little bit more involved than just dealing with a hole in the graph. So now let's look at piecewise functions and show how we do those. So we kind of treat them like left and right hand limits because the function is divided up into coming from the left, which would be this piece in our first function, and coming from the right of 1. So we want to look at it as two separate limits. So we would write it this way. So the limit as x approaches 1 for the left of g of x, and we're going to use the bottom piece because that is less than or equal to 1. is going to be the limit as x approaches 1 from the left of x plus 1. And since that's a polynomial, we can direct substitute and we get 1 plus 1, which is equal to 2. So that's the left-hand limit. Then we're going to do the same thing for the right-hand limit. So we're going to take the limit as x approaches 1 from the right of g of x. So that's going to be the upper part of the piecewise function there, because we can see that this says greater than 1. So this is going to be the limit as x approaches 1 from the right of x cubed plus 1. And again, it's a polynomial, so we can direct substitute. So we get 1 plus 1, which is also 2. And this is a great thing because the left and right hand limits equal each other. So we can draw a conclusion. We can say the limit as x approaches 1 from the left of g of x is equal to the limit as x approaches 1 from the right of g of x. Since they're equal, they're going to equal 2. Therefore, the limit of g as x approaches 1 of g of x has to equal 2. Okay, let's do one more of those examples. Let's do letter B. This time we're given h of x as our piecewise function, and we have that the left-hand piece coming from the left of 2 is the top function, and coming from the right towards 2 is the bottom part. And we're going to do the same thing. We're going to evaluate the left and right hand limits, and hopefully they will equal each other, so we can say that's the limit of h of x at 2. Okay, so let's start with the left hand limit. So the limit as x approaches 2 from the left of h of x is going to be the top function. So we are looking at x squared minus 4x plus 7. Using direct substitution, we get 2 squared minus 4 times 2 plus 7. And we get a 4 minus 8 plus 7. And that gives us a value of 3. Okay, now we're going to do the right-hand limit. So the limit as x approaches 2 from the right of h of x is going to be the limit as x approaches 2 of negative x squared plus 4x minus 1. So using direct substitution again, we get negative 2 squared plus 4 times 2 minus 1. We have negative 4 plus 8 minus 1. So the value here becomes 3 again. So we have just shown that the limit as x approaches 2 from the left of h of x is equal to the limit as x approaches 2 from the right of h of x, which is a value of 3. Therefore, the limit of h of x as x approaches 2 is going to equal 3. So that's how you handle piecewise functions. You treat them from the left and right hand limits. If either of these limits had been different from each other, let's say one of these was 3 and one was 4, then the limit of h of x at 2 specifically would not exist. Okay. So now what we have on this page are 3 examples of factoring and canceling out. So I will do 1 and I'll leave the other 2 for you to do. And same with at the bottom, example 4, I will do 1 and you can do the other one. A hint here, you might have to use a little information about knowing where the limit is to factor the bottom one. The bottom polynomial does not factor by grouping. So I would suggest using synthetic division. See if you can figure out what I mean by that when you get to it. But I will give you the answers to those. Okay, so let's go to the top here. So I'll do the first one. So what we have here is a limit as x approaches -2 of x squared plus x minus 2 over x squared plus 6x plus 8. So let's try direct substitution first. I'm going to do that down here. I know it tells us we're using the factoring cancellation method, but again, remember, you're not going to be told on the test or any of the tests or quizzes in class what method to use, so you want to make sure that you do try direct substitution first. And if I try to substitute -2 in, what I get is -2 squared minus 2 over -2 squared plus 6 times, that looks really messy, sorry about that, plus 6 times -2 plus 8. And when I simplify this, I get 0 over 0. So I'm going to have to do something else. So let's factor these. So I'm going to take the limit as x approaches -2, and the top factors into x plus 2 times x minus 1, and the denominator factors into x plus 4 times x plus 2. So the x plus 2's cancel. And that helps me because if I were approaching -2 before I canceled it, that's why I get the undefined form. So simplifying, I get the limit as x approaches -2 of x minus 1 over x plus 4. So now I'm going to try direct substitution. So I have -2 minus 1 over -2 plus 4. So I get -3 over 2, and I am done. Okay, again, pause the video and try to do letters B and C, and then I'll pick back up with example 4. Okay, here are the two answers for letter B and C. So we have 27 over 7 and 9 over 7. Now, moving on, let's do one example of what if we have complex fractions. What do we do with those? Okay, so what we want to use is the least common multiple over the least common multiple method. So in other words, what we're doing is we are simplifying the fraction and making it not complex. And then we can try direct substitution, and if not that, we can always try factoring and go from there. Okay, so again, you should always start with looking to see if you have an undefined form to begin with. So if we were to do direct substitution, we'd have 0 over 1/4 minus 1/4, which would be 0 over 0. So we're definitely going to need to do something. So here's what that something is. We're going to take the limit as x approaches 0, and we're going to take this complex fraction, and we're going to multiply it by the least common multiple, which is going to be 4. Let me use a different color. 4 times x minus 4. And remember, whatever you do in the numerator, you have to do to the denominator. Okay, when we simplify this, we get in the numerator 4x times x minus 4. And in the denominator, the first term becomes x minus 4. And the second term becomes x. So simplifying, we get feel like oh, sorry. That's not an x, it's a 4. That's why it wasn't working out. This should be a 4. From here, from that 4. I was putting an x there by mistake. Okay, so we get the limit as x approaches 0 of 4x times x minus 4 over x. And again, we can't do direct substitution yet because we have an x in the denominator, but the nice thing is we now have a common factor of x. So we have the limit as x approaches 0 of 4 times x minus 4. And now we can do direct substitution. And we're going to get (4) times 0 minus 4, which is negative 16. So that's our limit. Okay, so again, you try letter B. It's the same method, and then pause the video before you check your answer. So the answer to letter B is going to be negative 1/4. So hopefully you got that, and again, if you did not, we can go over it in class. That's going to be the end of part 2, and I'm going to finish this lesson in the 3rd video.